Hi and welcome back. Okay, in the last build video we put together these 16-bit counter registers, and at the moment I've just got the first one, which is the program counter, wired in directly, so we achieved the same level of functionality we had before we added these. I would note that in that build I wired the clock line here into the inverted rather than the non-inverted clock line, which meant that the response wasn't quite exactly right. That didn't affect anything too much at the time, but it would have caused us problems later on if we hadn't spotted that. Okay, so now we've got 5 of these counter registers, which means we've got 5 increment lines and 5 decrement lines, and at the moment we've just got the one increment line that is wired into the fetch unit here, and that is kind of chained off the clock, but then we've got this control line that's currently not wired into the pipeline, but if I raise that high it stops fetching so that the program counter doesn't increment and no instruction is fetched. So this is the control line that will sooner or later be wired into pipeline stage 2 to allow it to take control of the bus and read and write to memory. But that means we've got a total of 10 of these control lines for increment and decrement. This one is correctly wired, but I do want to have a look at that. But the rest of these, let's see if we can get them wired in. I did realise I made a little bit of a mistake sticking these lines temporarily into this piece of breadboard because it's the only real workspace I've got. So I'm going to stick this little bit of breadboard on the side to wire the lines into temporarily, and then I've got just that little bit of workroom to start the control for increments and decrement. Okay, I'm going to break with my own tradition and do a little bit of edit time narration here. Now, these LEDs on the GPRs are not behaving correctly, and I've just noticed that. The actual problem turned out to be a swapped around wire up here, which I found fairly quickly, but I did make a pretty terrible mistake. As always, when I spot a problem, I switch the clock from free running mode into single step mode, reset the processor, and try and step it to see where it starts to go wrong. And as you can see here, things are behaving very oddly. While I find the actual mistake I made quite quickly, there's a second problem on the board that I didn't realise. The clock circuit up here, I'd borrowed it the night before to work on another circuit, and I'd swapped some components around, and I'd actually made a very small error in reassembling it. I'd placed the capacitor back across the wrong pair of pins. Now the side effect of this is it worked fine in free running mode, which is why the build was operating correctly when we first fired it up, but I had broken the single step capability. So when I switched to that for debugging, I started to see all kinds of weird side effects, which I of course quite naturally assumed was a mistake I'd made on this board in the corner. Even though I'd found the actual problem I had created swapping the wires onto that daughter board quickly, I became distracted with the idea that there was another problem, and I was focused on the changes I had just made, assuming that the problem was there. So this is quite a nice reminder that first rule of troubleshooting program codes or circuits or anything really is check your assumptions. Because I went down a bit of a rabbit hole, ended up disassembling half the build trying to track the source of the problem, I really did kick myself when I tracked it down to just this little capacitor up here. Anyway, I got it all working again, and then the build can continue. Okay, so this is all working again. So 5 counter address registers, 10 control lines for the counters. We've got 5 increments and 5 decrements. It is worth having a quick discussion about where we're going to be doing increments and decrements from. So at the moment we've only got this increment line set up, which comes from the fetch unit here, where we increment the program counter apart from where this control line, which isn't actually hooked up anywhere at the moment, says that something else wants to access the main bus, so we can't fetch. Program counter needs to come down here from the fetch unit. We've already talked about how some of the increment and decrements need to be split for the stack pointer. In order to make the stack pointer work, we're going to need to do the increment and the decrement from different pipeline stages, although I've already said it doesn't really matter too much to us which way round. But I've got a couple of additional constraints on that. One thing is, I'd like all of the increments to come from one stage and all the decrements from the other, simply so we can talk in terms of increments here, decrements here, and not be having to further qualify that by which register we're talking about. It will just make it easier to think about and talk about. If for the stack pointer it doesn't matter too much, apart from declaring whether or not the stack pointer points at the last push item or the slot below it, the next empty space to push a value to, it's worth thinking about whether or not any other usage would cause us to want the increments and decrements to be in a specific location. And looking at where else we might increment and decrement a pointer, I'm thinking increment in pipeline stage 2 is actually the best idea, because I can see a number of situations where we might want an instruction that would increment a pointer after using it, but the case of incrementing before is less common, and decrementing before or after a value is not going to be as useful. So I'm going to put increments into pipeline stage 2 and decrements into pipeline stage 1. The increments are going to be split between pipeline stage 2 and the fetch unit, but decrements we can all put into pipeline stage 1. This up here are the 5 decrement lines, which number the registers from 0 to 4 based on the pins on this header, and I want to build a circuit that's going to handle the decrements. So just as we've done before, I'm going to use a 74LS138. So the 3 control lines are on the bottom left here. So these are now our 3 control lines for decrement. And now we want to take the outputs. And what I'm doing here is skipping output 0, so we can have a nice simple output which doesn't result in a decrement. I'm going to bring these out to a set of LEDs so we can see what's going on. And the outputs here are active high, which is good because that's what we want for the counters. But that does mean I'm going to wire these LEDs in upside down and common the resistor array to the 5-volt rail, so it gives us the results in a nice readable manner. And now we need to worry about the enable lines. So that's the first active low enable line. And that's the active high enable line. And we've got a second active low enable line right there. What are we going to do with that? If we were to say want a particular register to decrement every clock cycle, or we had back-to-back decrement instructions, we would expect it to happen each time. And the decrements and increments on the 193 counter chips here are technically an active high, but they expect the line to be held high most of the time, and then you bring them low and they increment or decrement on the rising edge. What we want to happen here is we want them to go low for half the clock cycle and then high for the rest of it. So what we're going to do is tie the clock into one of the active low enable lines. It's exactly the same as we're doing on the main bus load over here, so I can grab the same signal. It's actually in the inverted clock line. Okay, now the one thing we can't do is decrement the program counter, because when we tested the 193 counter chips, doing a count on both the increment and decrement lines together seemed to produce some weird results. I think it's undetermined behaviour, so we want to avoid that. Let's see what happens if we temporarily bring the second bit up. Okay, so our LED is flashing away. Let's slow that down. That looks pretty reasonable. It's a little bit dim. I'm going to swap in a different resistor array. Okay, so we've got 3 control bits. If we set them all to 0, nothing happens because we've not wired in that output. It's 4, 5. That's good. Let's bring in our control lines. So I'm going to drop the second bit, so we should start decrementing this register. I'll bring the first bit high, so then third register, third bit, and the first bit again. That's cool. So we've got nice simple 3 control lines. 0 means do nothing, and then 1, 2, 3, 4 and 5 will command a particular register to decrement. And decrementing the program counter is going to see less use, because we can't do that while we're actually executing code, but yeah, I think it's worth wiring them all in while we're here. So decrements, let's put that in there. Okay, I've got enough length of wire to here to tidy it up a bit, but I'll worry about that later. Okay, so increments. Right, now what I've got here is the 74LS139. This is very similar to the 138, but instead of a single 3 to 8 line decoder, it's got 2 separate 2 to 4 line decoders, which is good because we've got some of the increments we want to do here and some we want to do here. Now, stack pointer SI and DI we definitely want to do up here. And I know some people might think that there's not a lot of reason for incrementing the return address, but I actually see a reason that I will talk about in a future video why I might want to increment the return address from the fetch unit. If you think about that for a while, you might figure out what I'm going to do, but it's kind of one of those situations where I want to cover things one at a time, and that's going to be an interesting discussion enough to warrant its own video, which is best covered later on when we've got some more functionality. So at the moment we generate the increment line directly here, but I would like to generate it using half of this chip instead of this whole chip with a bunch of gates unused. So once again I'll put the LEDs straight in. Now by default we want to be incrementing the program counter here, so I'm going to put that into the first bit. And return address into the next. We'll bring the clock line across as before. And while we're here, I'm going to wire that same clock line into the second half of the chip. Okay, so now I need to disconnect the clock line that we hardwired in via this route. Deliberately broken there. So actually, while we're here, I'm going to wire in the other 3 increment lines. The low 2 LEDs here are increment, program counter and return address, and then we have a channel that is unused because we'll pull the lines down naturally. So then we've got stack pointer, SI and DI. DI at the bottom here is now incrementing away because the control lines have naturally floated high. Grab those control lines. Second pair of control lines for program counter and return address. Let's bring those down to our test location. Right, so now we've gone back to the upper 3 that we've wired into these 3 registers, not doing anything, and then the program counter is pulsing away because we've wired that into position 0, and that's what we've got selected here. Let's give this a try. So if I change that to 1, so then the return address is incrementing. We've broken the execution flow because that's not what the main processor is expecting. But that in program counter is incrementing, but if I change the second line, it all stops. So that is actually quite useful. That kind of mirrors the logic we were using here, in that if we raise this line, which is going to be our signal from pipeline stage 2 to say it wants control of the bus, we want to not fetch and not increment the program counter. So we can actually get rid of this chip now because all of its functionality can be replaced. So we've just got this control line that says whether or not we're wanting to gain control of the bus. So if I drop that in here like this, and drop this line low to signify that we are controlling the program counter. So we've got 1 bit to select program counter or return address, and 1 bit that we've now tied to the enable line on this line driver that controls fetching. So if we bring that line high, program counter stops counting and the fetch unit is dispatching zeros, i.e. NOPs, into the pipeline. So in theory the bus can be freed up for other memory accesses. Using the second half of this 193 to do the program counter increment is really good because it saves us a chip over here. And we have the added option of incrementing the return address. As to these 3 registers, we're currently selecting 0 on these 2 control lines. If I select 1, the over stack pointer starts incrementing. If I select 2, SI starts incrementing. And if I select 3, then DI starts incrementing. The names of these registers beyond the program counter is mostly arbitrary at the moment, but I'm going to try and start calling them what their intended use is. Now, of course, in many processors they wouldn't have counter registers for doing this, but the main reason why I've used counter registers here is because program counter needed to be one, and it's nice to be able to do the increments and decrements, particularly of the stack pointer, but these other registers the stack pointer, but also these other registers without having to shuffle stuff to the ALU, where we'd have to do 2 operations to do an increment on one of these registers, because the ALU is only 8 bits. But actually, in simple honesty, the biggest single reason why all of the 16-bit registers are counters is because this one had to be, and in a production processor design or electronics circuit design, you might want to simplify these for cost, even though you need the functionality here. For me, it was very much a case of design a PCB which had all of the functionality that I needed and then replicate it 5 times. So I'll take advantage of the extra functionality I've got. The controls for incrementing on these, they belong up here in pipeline stage 2. Okay, so that's all of our new functionality wired in, but we're not actually using it at the moment. Just got our shifting going on for a little test I wrote a couple of days ago. So let's have a think about what we can do with that in the processor. Okay, so let's add some new instructions to our architecture file. Decrementing the return address is something that we can do. I'm not going to put a decrement for the program counter in, because generally speaking we're going to be incrementing it, and any decrements on that are going to be when we've got the sequence logic knows it's not incrementing, and so I don't see any value to having it as an instruction. I'm going to start these at 30 hex. Once I've got a lot more instructions defined, I'll probably go through and pack them all down numerically, but I think spacing them out for now, just for neatness, is a good idea. So we've also got stack pointer SI and DI. Now it's possible we might not want to include instructions for incrementing and decrementing the stack pointer, because mostly that's going to be done with push and pop instructions, but we'll put it in for now. We do know that we're going to see some constraint on the number of different instruction permutations we put in here, because I've gone with an 8-bit opcode limit, so I'm trying to be reasonably careful. I think putting in instructions and then kind of trimming them down later if when we run out of space is probably the right way to go. Let's write some test code. We may as well start off by calling all of those instructions in sequence so we can see what's going on. I think what I'm going to do is continue with that same piece of test code we had before, but add an inc and a dec in there in the replicated code, just so we can see a few instructions working together. That's good. So now we need to add the implementation of those instructions back to the actual control logic. Right, so when we first assembled a file, one of the side effects of the assembler was to generate this header file, or update it from the previous version, so it now has the decrement and increment instruction opcodes declared for us. This is one of the ways I keep the control build and the assembler definition in sync. We need to add our control lines. So we've got those two control lines, sorry, those three control lines for the decrements in the 8th bit of pipeline stage 1, which is the 8th bit of our control word. So for here we're in the 8th and 9th bit of pipeline stage 2. So that's bit 24 and 25 in the control word. So for these opcode implementations, I've copy pasted the NOP because our control lines on here where we're selecting null for main bus load and main bus assert is the same. So then we just need to add to that the relevant control line that we've already requested. Replicate that out. Okay, let's see if that works. Okay, so we've generated the 4 bin files for our ROMs. Let's get those in. Okay, place your bets now on whether or not this thing works first time. Switch to single step mode. At some point we need to wire up the reset lines properly for all of these. Actually, I could do that now. So these are the 5 reset lines. Obviously what we actually want is it on the reset that comes from over here, but for now it's going to make testing a little bit easier. Let's reset it, clear out the pipeline. Once again, the logic to handle resetting the pipeline is something that I'd like to do fairly soon. But let's have a look at our code again. Okay, well, we expected an increment of the stack pointer there, an SI and DI. So I reckon when we're going to move on to these decrements, we're going to have done those the wrong way around. Okay, so this is 34 hex or 34 in hex. Let's go back and look. So that should be increment SP. So we're expecting this light to come on when I push the clock button. That's not what we got. Classic copy-paste failure. Okay, let's give this a go. Right, so here is the Inc SP. It's going to be processed in pipeline stage 2. So when I click now, it should do the increment. So following behind it is the Inc SI, which should come in here. Okay, this is interesting. So this is increment DI, which is about to move up into pipeline stage 2. But this is decrement RA, which is going to be processed in pipeline stage 1. So when we clock again, if everything's working, we should see an increment here to 1 and a decrement here to -1. So all the LEDs should come on here. Nice. So now we go through and decrement the stack pointer, so that should return to 0. Decrement here, and then here. Excellent. So now we're going to go back and we left that shift test in. We did add an increment and decrement into that. Yeah, that's working. Oh, that's really nice. Oh, this is interesting. Okay, so before we did the 4 shifts here back to back. But when these lights shifted off here, they were shifting in here. And that was because this shift immediately followed the shift here. So the value was getting shifted off through the carry flag, the logical carry flag, and back into the top. But now we go off and do our increments and decrements, and we're clocking the ALU at every cycle at the moment. And what we actually need to do is clock the ALU only when we're actually dispatching an operation into it. Otherwise, we're just going to have random inputs in here which are going to mess with the flags. So that's kind of interesting. It does actually show this problem before we build the circuitry to solve it. But no, we've got a big stack of extra increment and decrement instructions. So we're quite a nice little step further along. Okay, well that was pretty painless after the initial problems. So, okay, thanks for watching. Goodbye.